my name's Emily Johnson, Johnsson, and I'm a research geologist here at the U.S. Geological Survey Cascades Volcano Observatory.
Okay. And what's your specific area of focus?
Yeah, so what I'm interested in is using the rocks that we see erupted from past eruptions at the surface and using the chemistry and the textures of those rocks to figure out what was going on at depth before this magma made it to the surface. Where did it come from? Where was it stored in the crust? Where was it stored in the crust for how long? And what happened to it from storage to the surface? And really trying to piece together the eruptive history of all the past eruptions that we can to understand what we might expect from future activity.
Okay, tell us a little bit more about that history. I understand, Mount St. Helens has kind of gone through an evolution over time.
Yeah, yep, so Mount St. Helens has been very active in the last about 4,000 years, but we know it's been erupting since about 300,000 years ago. In the past 4,000, which is what made basically all of the edifice that we see today, it's had really variable eruption styles. So there were a couple of periods of activity starting around 3,000 to about 2,000 or so years ago where there was a lot of basaltic activity, particularly about 2,500 years ago. And these eruptions were much more similar to what is happening today. If you look at the eruptions from Kilauea, a volcano in Hawaii, and you see these big fire fountains and basaltic lava flows, that is what Mount St. Helens was doing for a fair bit of that time period. So if you go to Mount St. Helens today and you take a tour of the lava tubes, the 8th cave basalt, that was erupted about 2,000 years ago, and it looks very similar to the same types of lava tubes that we get on Hawaii. So there was a period of large lava flows that were very runny, much like Hawaiian basalts, but interspersed with these more explosive, stickier lavas that were erupting at the surface. And after that time window of more mafic or basaltic activity, it switched back into what we kind of know about Mount St. Helens today, having more of these larger explosive eruptions and forming lava domes of a different magma composition.
Okay, so what are some of the changes you see in the magma that makes these eruption styles so different?
Yeah, it's really the magma composition. So you can think of magmas as being sort of a continuum from a consistency much like maybe maple syrup through toothpaste. And Mount St. Helens 1980, 2004, that magma has higher silica content and is stickier. It's much more like toothpaste in consistency. If you look at Kilauea today and the older Mount St. Helens activity from 2,500 years ago is much runnier, much hotter magma, and it's lower in silica content. So that really affects how the volcano is going to erupt, what kind of style the eruption will be. St. Helens has a lot more of this stickier magma, more explosive eruptions. Kilauea almost always erupts this runnier, hotter magma, and that influences its eruption style. So what I like to do looking at the deposits is look at the composition, how much silica is in the magma, what types of minerals are present, and put all those pieces together to try to figure out, okay, what's the composition of this magma and what can the minerals and textures in there tell me about where this was stored at depth. So we know a lot about where the magmas today at Mount St. Helens are stored, but what we want to learn is, okay, has that changed over time? Do we expect Mount St. Helens to keep doing what it's been doing, or might there be a return to this older, different style of activity?
Oh, I was actually going to ask you about that. You're seeing it get thicker and stickier. Can it actually go back to this thinner?
Sure, it has in the past. So the first of these basaltic eruptions around 2,500 years ago followed a period of that same sticky dacite that is erupted in the current Mount St. Helens modern eruptions. So there was some of that dacitic, sticky lava, and then we had a series of basalts. So it's definitely possible for it to go back and forth. It has in the past, and there's no reason to assume it couldn't do that again.
Do we have an understanding of, you talked about silica content, kind of helping make this magma stickier. Do we know how that happens underground or where it comes from?
Yeah, I mean, we know some things broadly about all of our arc volcanoes and most volcanoes in general, that the magma feeding volcanic systems is generally that more low silica mafic magma, like the stuff that erupts in Hawaii. So that's sort of what we're starting out with. If that magma gets stored underground for a longer period of time, that's when this evolution of the magma can occur through crystallization and changing the composition that way through ingesting some of the rocks that the magma is sitting in, all of those take that magma from a runnier, lower silica composition to a higher silica, stickier composition. So it really is storage. We have to store the magma for a while to have that process occur.
Does that also translate to a longer time period in between eruptive events?
Well, that's a good question. Yeah, and that can be true. There are other factors, though, that impact how and when magmas make it to the surface. So part of it is, are they getting trapped and stuck in the crust and stored for a while? But there are also top-down factors. Like in 1980, there was a top-down triggering of the eruption when we had the removal of the edifice, and that sort of uncorked the lava, causing it to erupt. There are a lot of volcanoes that may be located along fault systems or fractures in the crust, and those fractures can help aid magma transport toward the surface. So there's a little bit of a top-down and a bottom-up story to why magmas actually make it to the surface and erupt.
Okay, let's talk a little bit about the magma coming up from below.
Yeah.
How is that magma coming up? Like, are we over a fault line? Is there a big magma pool? How is that working?
So in the Cascades broadly, we're located along a subduction zone. So that's where there's an oceanic plate that's sinking beneath the North American plate. And that creates this chain of volcanoes because as that oceanic plate sinks, it gets heated up and it starts to release fluids and melts from the plate. Those eventually rise through the mantle, through the crust, and erupt at the surface. That's why you get nice chains of volcanoes along subduction zones. You see this in Alaska, you see this in the Pacific Northwest, through Chile and South America. So all of these are subduction zone settings, and that's where we have continuous volcanic activity due to that process of making magma way at depth in the mantle. Now, how they get from the mantle to the surface, we can't see that process. We can only infer that looking at things like seismicity and the chemistry of the magmas and trying to piece together what their transport history was.
Are you able to get an idea of how much magma might be moving under Mount St. Helens, or is that also still kind of a mystery?
That's tricky, yeah. I mean, we can estimate how much has erupted in the past and use that to sort of back calculate, like, well, how much magma had to be feeding into the system if we saw this much rock extruded at the surface. It's easier to do that for past eruptions than really to see that going on today. It's actually very tricky to see magma stored in the crust. We see that better through things like seismicity and deformation, and we're able to model where the magma must be stored and how much might be down there.
Some people might say, why don't you just drill down and try to find it? Is that an option?
It is an option. They've tried that in places like Iceland, where they have drilled close to and intersected magma bodies there, but it's a very tricky business. There's a lot of heat coming off of stored magma bodies, and they're often stored at great depth. So we know from seismicity and from geochemical data from Mount St. Helens that the magma storage region is somewhere around 4 to 10 kilometers depth beneath the volcano. That's quite typical for many of our Cascade volcanoes, but that would require drilling quite deep into the crust to get at that. There are also inherent dangers of drilling into or near hot magma bodies.
Is there any clues that you've been able to discern that kind of give you a generally good idea of what you think might happen the next time Mount St. Helens wakes up?
I think the key is really trying to piece together what we think has happened in the past, and can we use that information if there was new unrest to say, okay, I think this might be a more mafic eruption or a runnier eruption, or I think it's going to be more like a 1980, 2004 eruption. And so part of what we do here is to study those past deposits and try to figure out where they were stored. So what I've been working on is looking at some of those mafic eruptions and using the mineral compositions and the gas compositions stored within minerals to figure out, okay, what depth were the basaltic, these more mafic magmas stored? And it turns out it looks like they were stored a bit deeper than the current dacitic magma body, which makes sense. You have mafic magma coming from the mantle at great depth and coming up through the system, so they're going to be coming from greater depths. So one thing we might learn from that then is, okay, if we see deeper seismicity than we typically do today at Mount St. Helens, maybe that's a sign that we have more mafic magma coming into the system, and we might expect a different eruption style. So it's really kind of combining our monitoring data with what we know from geochemistry about past eruptions.
Can we talk a little bit about some of the physical changes that we see on the exterior of Mount St. Helens once magma starts to move around?
Yeah, in 1980, of course, there was a lot of ground deformation. And back then, I don't believe we had any GPS instruments on the volcano. Today, we have roughly 18 GPS. So these are global positioning system, and they're basically measuring up, down, and horizontal movements of the ground surface. Before the 1980 eruption, there was this bulge on the north side of the volcano that you could see really well. And it was moving outwards right before the eruption at a rate of about 4 to 5 feet per day. So it was a very obvious change. Right now, we have instrumentation that can measure down to millimeters of deformation. So we could see the ground motion change or the ground elevation change really at higher detail than we could today, or could in 1980.
And you just touched on this a little bit. Can you go a little bit more in depth in how our ability to monitor these things has changed in the last 45 years?
Yeah. Well, for starters, we didn't even have the Cascades Volcano Observatory in 1980 prior to Mount St. Helens eruption. So the USGS folks that responded to that crisis were coming in from Denver and from Hawaii. It was only, I think, 1982 that this volcano observatory was established. So before Mount St. Helens started acting up, I think there was one seismometer on the volcano that grew rapidly during the 1980 crisis. But today we have something like 16 to 18 seismometers, 18 GPS, and constant gas monitoring stations. So Mount St. Helens is one of the best monitored stations in the volcanoes in the Cascades. However, all of our volcanoes are monitored to some extent, sort of commensurate with how active they've been and what we think their threat level is.
At what point can you say, we think this volcano is done for good? Is there a way to definitively say that?
Yeah, that's a really good question. I mean, right now, one of the things we look at is how many times has it erupted in the recent past? What is the recurrence interval? What is the time between eruptions? And has it erupted in the last 10,000 years? If a volcano hasn't erupted in the past 10,000 years and had very low eruption frequency before that, it's more likely to be deemed dormant or extinct. But it's really tricky, and having a great record of how frequently a volcano erupts so that you can kind of estimate, okay, is there a recurrence interval that's longer? So just because it hasn't erupted in the past 10,000 doesn't mean it's not going to. So not only is just a modern eruption, knowing that necessary, but knowing how frequently it typically erupts is also important.
In your time studying Mount St. Helens, have you discovered anything that surprised you?
Yeah, I mean, I think most people, think of Mount St. Helens and associate it with 1980, 2004 activity. This sticky dome, these very explosive eruption columns, and to go and look at the deposits in the field when you see these older deposits from 2,000 years ago and think to yourself, wow, this is Hawaiian. This is a Hawaiian-style eruption happening at this Cascade volcano that seems so different than the 1980 events. And trying to understand why it went through that phase of activity and what does that mean about the process of magmas making it to the surface at St. Helens and what to predict for future eruptions is really fascinating.
And has that change in eruptive and magma styles kind of been a characteristic seen throughout all the Cascade volcanoes, or is it specific to a few?
It's more unique to St. Helens, actually. There are some Cascade volcanoes, like Mount Hood, for example, that erupt pretty monotonous or very homogeneous compositions. They don't change a whole lot. And the style of eruptions don't change as much. St. Helens is a bit unique in having these really diverse eruption styles and magma compositions.
Right. Mount Hood is another volcano we can see from our backyard. And you just elaborate a little bit more on its style. Since we have ski resorts up there, it's something people drive over every day.
Yes.
So what are we looking at with Mount Hood?
Yeah, and Mount Hood typically erupts more sort of intermediate magmas in between our mafic, basaltic, and our dacitic compositions. It doesn't have as many explosive eruptions by far as Mount St. Helens does. It does have that same lahar potential, so those volcanic mud flows like we did see at Mount St. Helens, and that sector collapse, the collapse of the flank of the volcano. Those are similarities between St. Helens and Mount Hood. But the recurrence interval, the frequency of eruptions at Hood is much lower. And again, not as many explosive eruptions and different magma compositions.
Can we go back to the sticky versus more liquidy magma? Can you elaborate a little on how stickier magma equals more explosive eruptions?
Yeah, so I think the best way to think about it is if you have a toothpaste, a tub full of toothpaste, you have a tub full of runny maple syrup, and you try to get bubbles to flow through those. Bubbles can flow through and escape a runny or more fluid liquid, right? So that's kind of what's happening at Kilauea. You can imagine sort of holding your thumb over the nozzle and it's getting this sort of foamy water that's coming out. That's basically what fire fountaining is at Hawaii. So they have lower gas contents and the gas is much easier to escape. So it's not going to build up pressure and explode. If you try to imagine gas getting out of a toothpaste-like liquid, it's very tricky. And eventually in some volcanoes, the pressure builds up, the gases will eventually break through that sticky magma more catastrophically rather than just degas or come out with this more fluid magma. So gas content of the magma, how much gas there is to begin with, plus how sticky it is and how easy it is for that gas to get out are really two critical aspects of what drives volcanic explosivity.
Great. And how did you get into this field?
Yeah, as a kid, I loved volcanoes. When I was very young, I saw a Reading Rainbow episode about Kilauea. It must have been about 1985 when Kilauea was erupting and had these gorgeous fire fountains. And LeVar Burton was standing there with a USGS scientist. It was a woman scientist that he was interviewing about this fire fountaining at Kilauea. And I was awestruck. And I just couldn't believe that this was happening like right now somewhere in the US and that you could just go see this and that there were people working on this. This was a job that you could have. And then I think like many people, I went through the rest of my education and never heard of geology again. So it wasn't until I got to university and I took a geology class kind of on a whim and remembered, oh my gosh, yeah, this is amazing. And I think for me, volcanoes kind of they straddle the line between creation and destruction, right? So they are creating new earth, they're creating new land all the time, but they're also destructive and powerful in a way we cannot control. So it's this really sort of interesting balance between those destructive and constructive forces and wanting to help understand them better so that we can prevent loss of life and loss of property during a volcanic eruption. The better we understand what volcanoes can do, the better prepared we are for future activity.
And is there any message you'd like to give just to the people who live around these volcanoes?
I think one thing that's really important to know is that we will see run up to eruptions. There is not going to be an unexpected, out of absolutely nowhere eruption tomorrow from any of our volcanoes. If you look back at 1980, we know that there were earthquakes occurring months before the eruption, and they gradually increased. We've seen that in many other volcanoes throughout the world, right? So it's not going to be an out-of-nowhere eruption. We are doing a good job of monitoring these volcanoes, and we will see changes, and we know what the background is. We know what normal is for Hood. We know what normal is for St. Helens, and we'll see something out of the ordinary. I think another thing just for folks to think about is that mountain on my horizon a volcano? In Portland, that's true for many things. Even the smaller volcanoes throughout Portland, like Rocky Butte and Mount Tabor, those are old little volcanoes that are right within city limits. And just being curious and trying to get to know some of our nearby volcanoes is important.
Okay. Speaking of Mount Tabor and Rocky Butte, are those ones we might still consider active, or are they in the dormant, or?
No, they're part of a volcanic field, and this is actually another area of interest for me and where I do a lot of my research is in what's called distributed volcanism. So instead of having a central vent that erupts many times and produces a large, long-lived volcano like St. Helens or Hood, you can also have magma that pops up to the surface in little one-off eruptions. And that's what Mount Tabor, Rocky Butte, and those volcanoes represent. This is called the boring volcanic field, named for Boring, Oregon, not because the volcanoes are boring, but there are dozens and dozens of these little tiny volcanoes. They erupt one time and one time only, and then a new volcano pops up somewhere else within a field of many vents. And while the boring volcanic field in Portland hasn't been active in quite some time, I think the most recent eruption was 68,000 years ago, there are other volcanic fields in Oregon that have erupted very recently. So if anyone's driven the pass, Mackenzie Pass or Santiam Pass, and you cross those lava fields, that is a distributed volcanic field. There are small volume, one-off eruptions there, cinder cones and lava flows that erupted very frequently for a couple thousand years, up to about 1,500 years ago. So really young, small, one-off eruptions. And I think the thing about those that are tricky is that they're sort of a one-and-done eruption, but you don't know where the next one's going to be. So for a lot of the volcanoes we work on, like St. Helens, we have a pretty good sense. If there was activity, it's going to roughly come out somewhere near the vent or on the flanks of that volcano. Within these distributed fields, you don't know exactly where the next one of those vents could open up.
But do we still have the ability to kind of pick up on the warning signs for those ahead of time?
Yeah, just like any of our other volcanoes, magma moving through the crust will produce seismicity or earthquakes. We would expect to see deformation, the ground surface moving up. So we would still see all of those same warning signals. And at that point, we might be able to decide, okay, I think the next volcanic eruption might be in this region over here.
Okay. So let's say you do start to get those signals. What are your next steps, not just here at the observatory, but in a broader impact to address what could happen?
Yeah, I mean, of course, there will be steps folks are taking here to understand what we might expect from the eruption itself. But another key thing is talking to the community and making sure the message is getting out about, what is going on. At a place like St. Helens or Hood, I think people are generally more aware that they do have a volcano in their backyard. In places like Central Oregon and some of these distributed fields, it's a little trickier to say, hey, these little guys are actually, those are volcanoes. They look like little hills on your horizon, but they're volcanoes too. And so I think the more we can talk about and just create awareness about what types of volcanic hazards exist and what types of volcano eruptions you might expect in the future, all of that is important work to do. So the U.S. Geological Survey, our observatory, or any of the observatories, should there be an increase in activity, like the current increase at Mount Spur, the Alaska Volcano Observatory released an information statement describing what has changed. We are seeing more earthquakes. They are occurring at this frequency, at this magnitude. We're seeing deformation occur. We are seeing melting of the glacier and the formation of a hot lake at the crater. So all of that information goes out to the public and is widely available. So we have our own information statements for the Cascades volcanoes as well, should there be an increase in activity at any of them.
I think we had one of those recently with Mount Adams,
yes.
Did we not?
Yeah, yep. That was back in, I think it was September of 2024. There was an increase in the number of earthquakes we were seeing per week at Mount Adams, beyond background activity for Adams. So at that point, it warranted us putting out an information statement to alert the public and stakeholders to the fact that this was happening and that we were keeping a close eye on it, put out new instrumentation on Mount Adams to try to look at and make sure we're capturing all of the earthquakes that were happening. Things died back down, but that will always happen in the event of an increase in activity.
And so we've been talking a lot about how there's been widespread volcanic activity all around our region. Is it a large kind of like interconnected underground magma system, or is each kind of volcanic system its own individual entity?
Yeah, it's more the latter. So each volcano has its own unique kind of plumbing system, if you want to think about it that way, with magmas coming up all the way through the crust, maybe having some storage in the crust and then up through the volcano. But each one of those is a separate system. Mount Rainier has its own system, St. Helens, Adams, Hood, etc. So there is, and in the distributed fields as well, there are single off kind of little soda straws, if you want to think of it that way, of magma that make it through to the surface and then they're done. But they're not interconnected with the broader pool of magma at depth. Yeah, so we've got an assortment of rocks and some ash, all from Mount St. Helens, from different eruptions. So you'll notice first off the very sort of light color of all of these rocks, right? So this is a very light whitish color to sort of more medium gray, but they're all kind of the same composition. So this is our Mount St. Helens dacite, which has higher silica content than sort of a basaltic eruption. The differences in texture tell us something about how these were extruded or erupted from the volcano. So this rock here is full of bubbles, and it's actually, for its size, quite light. And this is a sort of pumiceous rock from St. Helens that is full of trapped bubbles, which gives it its light weight. On the other hand, some of these are sort of dome material from Mount St. Helens. These are the sticky lava that was sort of oozing slowly out at the surface. You can't even see bubbles to the naked eye, whereas you can clearly here. This is a much denser, heavier rock, but it's the same composition roughly. The other product that's come out of Mount St. Helens, so these would be sort of the dome-forming eruptions. This would be a more explosive eruption, but we also have fine ash particles here, so this would be what is sort of floating up and being ejected through that eruption column. So in the analogy of the sort of 2-liter soda bottle for magmas is you can dissolve gas in a liquid, right? So you can dissolve CO2 in a 2-liter of soda. You take the cap off, you go from having no bubbles in your bottle to tons of bubbles. If you take the cap off really fast, it's going to spray all over. And if you shake it up before you take the cap off, it's going to spray even more. So the more bubbles you have growing in a liquid, the more it's going to expand the volume of the whole material, right? So if you have dissolved liquid, it can take up a certain amount of space. If all of a sudden you have exsolved gases in there too, it's going to expand and explode if those gas bubbles can't get out. So that's kind of what this series of separate rock samples represents. These are the finely fragmented bits of ash that get exploded. This is a larger, frothier bit of that very bubbly magma that got exploded out of the volcano. The dome-forming eruptions we've seen at St. Helens typically come kind of after we've had a big explosive event, or in the case of the 2004 to 2008, it was just erupting the sticky lava dome mainly. And that's a very degassed magma. It doesn't have a lot of bubbles in it. It's just sort of slowly oozing out at the surface.
Is there a way to monitor how much gas is building up inside in addition to the magma?
Yeah, that's a great question. So one thing we can do is look at how much gas emissions are coming out of the top of a volcano. And we can sort of track those over time, like seismicity or any of our other monitoring data sets. We want to have a baseline. And so if we know, yeah, there's some amount of gas that's typically coming out of this volcano, if that goes up or down, both of those things could signal something to us. If it were to go up, maybe that means we're getting an increase of new magma, fresh magma in at depth. If it stops, maybe something has capped the system and we are no longer letting those gases get out. So any changes from background are important to understand and try to figure out what's going on with the volcano to change things.